What is up, guys? I've been down and out for a couple days now, maybe closer to a week for you guys. Computer clapped out on me and finally got it back up and running. So if you guys are interested, let's jump into some circuits today. Alright guys, welcome back to another episode in our circuit design series. Today we're going to be going over MOSFETs, specifically for in-use in switching circuits. We're going to be working with two different types of MOSFETs. N-channel is seen on the left, and P-channel is seen on the right. N-channel FETs are used to switch the low side of a circuit, or in other words, the negative ground side of a circuit. P-channel FETs are used for switching the positive side of a circuit, or the high side of the circuit. The idea here is that whatever your load is, whether it be a motor, solenoid, LED, etc., that one side is connected directly to the positive or negative, and the drain of the MOSFET is switched to complete the circuit and allow power to flow to your load. Each MOSFET has its own specifications and ratings. We will be focusing on logic level FETs today, meaning you can switch them on and off with low level logic, which is exactly what microcontrollers output. And depending on the chipset, it's somewhere roughly between 3.3 to 5 volts. Here we can see two data sheets from examples we will be working with today. The AO3400, an N-channel FET, and the AO3401, a P-channel FET. These are an SOT23 package, which is a relatively small footprint. Looking briefly at the specifications, we can see the VDS of 30 volts. This means we can output a maximum of no more than 30 volts. So if you're trying to energize something over that, this would not be the correct choice for you. They also have a relatively low RDS, meaning there's minimal voltage drop across the MOSFET, and there's also minimal heat generated. They can handle between 3 to 5 amps of continuous current depending on which of the two you're using. Now let's go ahead and jump over to EasyEDA and drop some basic switching circuits with these FETs. Alright, so jumping back over to EasyEDA, I'm going to jump right back into our LDO circuit schematic. That way we can continue to add blocks to the schematic. So what I recommend you guys do is jump over to lcsc.com like I did in the previous series video, and go ahead and choose your components in whatever package that you want them in. I'm going to be working with SOT23, so I already have my part numbers saved from lcsc.com. And I'm going to go ahead and start inputting those right now and adding those parts to our drawing here. So right off the bat, let's go ahead and grab our 3400 MOSFET. Let's grab our 3401 MOSFET. We're also going to need some pull-up resistors. A 10K resistor, 1/8 of a watt, is going to be fine for this application. Go ahead and choose that again in whatever footprint you like. I'm a fan of the 0603 footprint. So that's what I'm going to go ahead and be working with today. This is funny. It's asking if I want to update for a resistor. I really don't. A resistor, you can't really go wrong. It's just two pads. So, alright, we got our 10K resistor here we're going to use for a pull-up. And then we also are going to want to grab a smaller resistor. We're going to go with a 22 ohm in this scenario here, and I'll explain why as we place the resistors. Okay, so now that we have all of our parts, I'm going to show you guys how to build first the N-channel MOSFET. So you want to go ahead and place your net flag for ground on the source, okay? And then you're going to want to go ahead and take your resistor over here. This is going to be a pulled down resistor. I'm going to place it right here. I'm also going to just move these guys over and begin the organization from the beginning. And then we also need to tie this resistor to ground because it's a pull down resistor. You can choose to use a wire and connect it. Me personally, I like to just go ahead and grab the flags. So I'm just going to copy and paste. And then we're going to go ahead and place a net port. It's going to be an output port on the drain. And what we're going to call this is GN ground output. Okay, so for simplicity here, we have the source on our N-channel MOSFET is ground because that's what an N-channel MOSFET does. We have a pull-down resistor, which means it's a weak amount of ground that's actually coming into the gate of this MOSFET. And the purpose for that is to keep the MOSFET in the off position so that over here at the drain side where it says ground output, this ground output is actually floating. It doesn't have any sort of output coming out of it at the moment. Now, the way that we're going to get output from that guy is with this little resistor over here, and it's not technically required, but this is going to be a current limiting resistor, so if something was to happen on our gate side here, some sort of backfed voltage or something, the idea of this 22 ohm resistor is to protect our microcontroller because I'm going to be tying our microcontroller to the gate over here. So again, I'm going to go ahead and place another net port, and this time it's going to be an input. And I'm just going to call it GPIO1 because most microcontrollers are going to have GPIO as the default labeling on them. So the concept here is, as I said, this N-channel MOSFET is currently in the off position. To turn it on, our microcontroller output, which is GPIO1, would have to send a high logic, which would be, in this case, 3.3 to 5 volts, whatever the microcontroller is rated for. Now when it sends that, it's going to overpower the weak pull-down resistor here, and it's going to give a positive voltage to the gate. When a positive voltage comes to this gate right here, it's going to be higher than the source, which is ground. When that happens, it energizes the MOSFET and allows the source, which is ground, to come through and come to the drain side, which we're calling ground output. So this would now be grounded at the output. Let's look over here at our P channel. Let's go ahead and place a 5 volt flag on the source. Let's go ahead and do our resistor. And in this case, to turn the P channel off, we want to go ahead and bring a positive voltage over to the resistor. So we don't want a pull down resistor, we want a pull up resistor. So I'm just going to go ahead and copy that net, paste it again, and there we go. We're going to place a output flag, or excuse me, an output port. And we're going to go ahead and call this 5V output. Now, for argument's sake, let's go ahead and assume that our microcontroller is working at 3.3 volts, right? We drew up a 3.3 volt regulator. So let's assume that our microcontroller wants 3.3 volts. If we have a 5 volt pull-up resistor right here, that means we have 5 volts across this resistor. If I was to bring another GPIO over here, like we did here, and plug it in, we would actually have issues because you are now introducing 5 volts to the microcontroller's logic, which can only handle 3.3 volts. So you could damage the microcontroller by backfeeding it. Now, it can seem a little counterintuitive because earlier we were talking about how these MOSFETs can handle up to 30 volts. Well, let me show you how to turn on a P-channel MOSFET with an N-channel MOSFET. Because it's an N-channel MOSFET and it is a ground reference MOSFET, it means that all we're doing is essentially using our reference, which is 0 volts. And when we have a 0 volt reference, that's safe with a 3.3 volt microcontroller because it's below 3.3 volts. So we can always connect a 3.3 volt logic microcontroller to an N-channel MOSFET without issue. Now, to turn on this P channel, it's actually really easy. What we're going to do is we're going to go ahead and place a net port in. And we're going to name this guy ground output. Okay. So what happens here? When we send 3.3 volts from our microcontroller, it comes through here, overpowers the 10K pull down, the positive voltage reaches the gate. The gate now has a positive voltage, which is higher than source, which means this MOSFET is on. The ground can come up, and now this ground output is live. It has a ground on it now. That ground output is connected over here to this gate that also has a 10K pull-up that's on 5 volts. Well, it's isolated through the MOSFET, so we're not going to be getting 5 volts to come over here into this other side over here. It's isolated. When this ground comes over to the gate, we are now seeing a voltage that is lower than our source. And on a P-channel MOSFET, that means it will activate and turn on. So now our higher 5 voltage reference on the source is going to flow through to our 5 volt output. So this configuration right here can be used for up to 30 volts. So why don't we go ahead and assume that we have a 24 volt logic. You can actually, using a microcontroller in this dual MOSFET configuration exactly as I'm showing you, you can actually use that microcontroller with a low logic level to turn on and off a 24 volt signal to your load for a motor, an LED, whatever it is you're using. So now let's go ahead and block it out just like we do the other ones. We're going to go ahead and place text, part number. That's just how I do it. You guys don't have to build your circuits like me. This is just the Solomon way. This is your boy's way. And then our resistors are labeled clean. I don't like how sometimes when these parts drop you get like a U. The default for MOSFETs and transistors is typically labeled as Q. So I'm going to leave this one labeled Q1. I'm going to come over here and I'm going to rename this guy Q2 to keep our schematics more in check. with EasyEDA, a lot of people upload these parts into here, and so sometimes there's just little flaws and stuff like that to look out for. Now I'm going to go ahead and copy this text. I'm going to paste it up here into the top, and we're going to call this a logic level high voltage output switching circuit. Okay, and I'm going to go ahead and put this back to a 5-volt configuration. I was only using 24. You can put whatever you guys want on here, but eventually we'll go ahead and maybe do something with all this stuff. So we've gone and built out this block. We can stick it right over here. And there you have it. You now have 2 blocks to work with inside of your EasyEDA. You're going to be getting a little bit more comfortable now, hopefully, with building out some circuits. And this is a lot cleaner way to do this. It doesn't have wires going everywhere. When I say wire, if we look over at our dropout regulator, you can see there's a wire between tab and the output, because these are both actually outputs. They need to be linked to each other. So that's a wire. You can always use a wire if you want, but I personally just find it cleaner to use ports like this, especially when you start building big schematics. It just makes a lot of sense. So don't forget, you guys can copy whatever parts are in here. So now you have access to your 10K resistors, 22 ohm resistors, you have access to your MOSFETs, you have access to some standard caps and whatnot over here. We have diodes in our circuit, and something else we can do to further refine this a little bit more. We can go ahead and actually bring this down. And then I'm going to actually just go ahead and delete this wire, this green part. They're called wires. And I'm going to grab one of my diodes that I like to use. I'm going to copy that guy and drop it in right here. Connect my port. Okay, now why did I do this? This is going to allow the voltage to flow out in one direction, and it's not going to flow back in. So a little bit of protection now in the circuit there, but anyhow, you guys now have a regulation circuit, you have some MOSFETs to play around with, and in the next series we'll go ahead and draw up a microcontroller circuit. I hope you guys learned something from this. I'm sorry if it's kind of all over the place or I'm saying some things that aren't clicking. If you have questions, please drop them below in the comments. Other than that, I will see you guys on the next one.